my student. Okay, and my student Jeru Shan. It's also building on a series of earlier work on Wilson lines in an equal force pyramid, so I'm not gonna write all of them here. I'm just listing the various collaborators. Okay, so for this audience, I don't think I need to say much about the review of thermal correlators, just very briefly. So in holography, finite temperature correlation functions have been studied extensively, since the early days of ADS-CFT. So the general picture is that if we want to describe the CFT at finite temperature, the boundary of ADS, we have a black hole in the space-time, so we consider asymptotically ADS black hole. And the leading order at Large-N and strong coupling from CFT point of view, quantities like thermal two-point functions can be computed essentially by solving wave equations in this space-time. And one remarkable feature of holographic thermal correlators is that in some cases, features of the black hole interior can be encoded in analytic structure of the correlators and vice versa. One recent example is this paper by Grimberg and Maldacena, where they argue that the proper time to the singularity is encoded in thermal one-point function. Another older example, which is more relevant to this talk, is this observation that dates back to these papers, that geodesics that connects the two boundaries of eternal ADS black hole and in some sense bounce off the black hole singularity. The contribution of such geodesics is reflected in certain singularity of the two-sided thermal correlators, which are sometimes called bouncing singularities because of the relation to these geodesics. This bouncing singularities have been studied also more recently, where a deeper understanding of them has emerged. One direction was these papers where they introduce a thermal product formula that gives the thermal correlation functions in terms of quasi-normal modes, and they show, among other things, how the singularities arise from the asymptotic behavior of the quasi-normal modes. And another important development are these papers by Nak, Hongliu, Parnachev, and Valak, where they showed that from the CFT point of view, these bouncing singularities are essentially controlled by the multi-stress tensor OP coefficients in the large N limit, where N is the power of the stress tensor. And also, as discussed quite recently, while all of the previous work on this mainly focused on two-sided correlators, in this recent paper, it was also argued that the singularities also show up in more standard one-sided observables like retarded correlators, and they are basically reflected in non-perturbative terms that appear in the large frequency expansion in the regime of large real frequencies and fixed scaling dimensions, which can be analyzed using a WKB approach. So in this case, the WKB works because of the large frequency limit, and it's not necessary to take the scaling dimensions to be large. Okay, so the focus for this talk will be indeed just on retarded correlators. So the standard retarded correlator in finite temperature CFT is defined like this as the expectation value of the commutator, where theta is the step function. And it's often useful to analyze this in the frequency domain by doing the Fourier transform. So the Fourier transform goes from 0 to infinity because of the theta function. And I'll review this in more detail later, but just before we get bogged into the details, I want to give a general kind of overview of the main points. So the way you compute this kind of quantities holographically is that you solve the wave equation in some planar ADS black hole space-time. If you're interested in the finite temperature theory on flat RD minus 1, you take this planar black hole where f of r is this familiar function where RH is the position of the horizon and it's related to the temperature in that way. And to find the retarded correlator, the standard procedure is to solve the wave equation with the infalling boundary condition at the horizon, and then take the ratio of the normalizable and non-normalizable modes, as I'll review more detail later. Okay, so just to give an idea of where we're going, let me just start by summarizing the main point. What is the structure of these retarded correlators in holographic theories at large frequency? So the large frequency behavior is controlled essentially by zero temperature physics. The leading term is the zero temperature result, which is just the power of omega, which is fixed by the scaling dimension of the operator. And then the structure is as follows. So there is a series of corrections in inverse power of omega. Here I'm specializing to the case of d equals 4, which will be the main focus in the talk. And then one can see that this series goes in powers of in 4 powers of omega. So omega to the 4, omega to the 8, and so on. And this expansion, this series here, which is an asymptotic series, is basically controlled by the OPE, as I said before. So these coefficients are related to multi-stress tensor OPE coefficients. And then there are non-perturbative corrections suppressed as e to the minus beta omega. And these non-perturbative corrections are the ones which are directly related to the bouncing singularities and can be computed as shown in this recent paper by this WKB analysis that I mentioned before. While this perturbative series can be computed order by order in a near boundary expansion, following the method that was originally in this paper by Fitzpatrick and Wang. And remarkably, what happens is that the large order behavior of this perturbative asymptotic series actually is precisely consistent with this non-perturbative term. So as it's familiar with the theory of Borel summations, for example, large order behavior of asymptotic series is connected to the non-perturbative parts of the whatever function you're studying. So we'll explain this in more detail later. And so just to recall this picture of the bouncing geodesic, so in the two-sided setup, when you study two-sided correlator, this kind of non-perturbative corrections here are the ones which are related to this bouncing geodesics. We can view them as e to the I omega delta t, where delta t is the time shift for a null geodesic that bounces off the singularity of this two-sided black hole. Sorry, I'm not seeing my slide very well. There's something covering it. Okay, so if you compute the time shift for this in this picture for this null geodesic, the time shift in that geometry is computed by this integral, which gives this complex time shift beta over 2 1 plus I, which we will call TC for later in the later parts of the talk. And the imaginary part basically arises from the fact that we have to include an I epsilon prescription when we integrate around the horizon where this F vanishes. Okay, so this geodesic picture explains essentially the structure of these non-perturbative corrections, but it's only qualitatively correct because in fact, if you look at the WKB analysis, it breaks down if you're near the singularity, and the calculation there has been done more carefully. And in particular, just the computation, this time shift doesn't tell us anything about this coefficient R, which we may call a reflection coefficient, which is what multiplies this exponential. So a more careful calculation, which I'll do not in the context of two-sided, but in the context of retarded correlator, will allow to extract this and also this reflection coefficient. Okay, so what's the relation to the singularities? That basically that just follows from the Fourier transform. Once you realize that the retarded correlator in frequency space has these non-perturbative tails, these non-perturbative corrections that go like this, e to the minus beta over 2 1 minus I omega, which we can call e to the I omega TC, then by Fourier transform, going back to the time domain, there will be a contribution which goes like 1 over t minus tc to some power. And that's the singularity in the complex time domain, which we may call a bouncing singularity. Okay. Any questions so far? Feel free to interrupt if I'm going too fast. I'm assuming that people are really familiar with this stuff even more than me, so I'm going fast. Okay. So that's a brief overview of this concept of bouncing singularity and how it's related to the large frequency behavior. We will go back to this in more detail later in the talk, but now I want to overview the second player in my talk, which is defects. So the main idea is to try to understand how these holographic correlators behave in the case of defects. And most studies of holographic correlators so far focused on usual case of local single trace operators, which are dual to bulk fields like scalars, gauge fields, and graviton. But in QFTs and in CFTs, in addition to local operators, there are a variety of interesting non-local objects, which we may call generally defects, like line operators, surfaces, interfaces, and so on. In particular, in CFTs, a special kind of defect, which is the one I will mainly be interested in, are conformal defects, which are defects that preserve a subgroup of the conformal group. So, for example, if you have a p-dimensional conformal defect, it preserves a p-dimensional conformal subgroup of the full conformal group of the full CFT. And there are many explicit examples where one can find conformal defects in familiar CFTs, like boundaries and interfaces in various systems like ON model and Grosnoval model, which also admit various kind of line operators, uh, surface operators, monodromy defects, and so on. And another more familiar example, perhaps, which has been studied for a long time, is the case of Wilson lines in gauge theories. And in case of conformal gauge theories like n equals 4 superior Milsway BJM, we can have conformal line defects. And this will be the main focus for this talk. So in the presence of a defect, in addition to the usual local operators that you can still insert away from the defect, the usual CFT operators, there is now an additional set of local operators that live on the defect and describes the local excitations of the defect. The most basic example is the displacement operator, here denoted as D, which describes transverse deformations of the defect. So in this picture, the plane is supposed to describe the full CFT. Then we consider a line defect in that CFT. And if we want to study the deformation of that line defect, that can be effectively described by studying correlation functions of some operators that live on the defect, which are called displacement operators. And the structure of the correlation functions of operators inserted on the defect is basically constrained by the conformal symmetry preserved by that defect in a way which is similar to CFT. It's just basically a lower dimensional version of a CFT embedded in the larger CFT. Now, the full structure of the defect CFT is much more rich because one can also consider, in addition to things inserted on the defects, also operators away from the defect. And those have a very quite rich structure. But for this talk, I'll focus just on insertions on the defect itself. And then the structure is basically similar to that of a CFT, but restricted to that submanifold of the CFT. Okay, so these systems of conformal defects have been studied extensively at zero temperature. There are a lot of papers about it, but finite temperature cases have been studied much less. There is one exception, one recent example by people here, some of them in the audience, by Julian et al. In 2024, where they studied line defects at finite temperature. So in this talk, I'll also focus on line defects, as I said before, on Wilson lines, but I'll focus in particular on the holographic calculation of these correlators. So I'll take a Wilson line in finite temperature n equal 4 superior mils and study the correlation functions in that system holographically. So this kind of operator at finite temperature, this Wilson line at finite temperature, has a clear physical meaning. It just describes the Wilson line itself describes a heavy probe charge, and then we put that probe charge in the finite temperature gauge theory and study correlation functions of things like displacement operator basically describes how that probe charge reacts to the transverse forces in the finite temperature plasma. And the natural question is whether thermal correlators of displacement operators in this setup also has similar signature of bouncing singularities, like the case of the usual operators, single trace operators, local operators. And well, of course, the answer is yes. Otherwise, I wouldn't be giving this talk. But we'll see how that comes about. Okay, so just to give an idea of how the holographic calculation works. So the Wilson loop is dual to a fundamental string in the holographic dual, some string worldsheet. And for the finite temperature theory, we have to find the dual string in the planar black hole background if we work with the gauge theory in the flat space. And the dual worldsheet is basically just an ADS2, asymptotic ADS2 subspace of the planar black hole background. It's just a worldsheet that extends along the time and radial direction. So is it itself the geometry of that worldsheet is itself some kind of black hole in the sense that it has a horizon which is just inherited from the bulk geometry. And to compute the retarded correlator in this setup, one is just supposed to study the transverse coordinate fluctuations of the string by using the Nambu-Goto action, which essentially will boil down to solving wave equations for fields propagating in this two-dimensional geometry. And then the same methods that have been used for the usual bulk scalars, which are dual to local operators, the same methods can be used here, in particular the WKB method of Afghani-Jedi et al. Can be extended to this case, and also the asymptotic OPE or near boundary expansion can also be done in sort of the similar way in this setup. Okay. Okay, so as I said, the main result is that this holographic thermal defect correlators also display bouncing singularities, and the bouncing singularities are at the same location, the same value of TC as the case of the local operators, dual to bulk scalar fields, with different details. For example, the reflection coefficient will be different. Before describing that calculation in the case of the defects, it's useful to first review the case of the bulk scalar fields and try to go through this WKB approach of this paper by Afghani-Jedi et al., which is somewhat involved and conceptually a little bit complicated. But because I'll use exactly the same method for the case of the defect correlators, I want to start by reviewing that. And then adapting to the case of the Wilson line is basically straightforward. I saw that you already had a talk by Simone on this some time ago, so he probably already explained a little bit how that works. But let me go through that. Before actually doing that, let me just review some basics, just to give some definitions and notations about the thermal correlators. Now, just in the case of usual local operators in CFT. So if we start with the Euclidean theory, where we have the thermal circle, the usual thermal Euclidean two-point function is just this one, where T denotes the Euclidean time ordering. And then to go to real time, we can define the Whiteman functions as usual by analytically continuing these Euclidean correlators. And the Whiteman function basically give the real time two-point function with the two orderings, either this or this. And from the Whiteman functions, one can get the retarded correlator as the difference of the two Whiteman functions, which give the commutator. And the Euclidean thermal two-point function, as is well known, admits an OPE expansion. We basically can bring together the operators using the OPE, and then this two-point function reduces to a sum of one-point functions, where these are some Gegenbauer polynomial, and eta is given here on the side. This OPE simplifies considerably if one takes, for example, x equal to 0, like take the operators to be at the same spatial position. And the structure in that case looks simply like this, as a series in powers of tau over beta. And this is basically also how the OPE will look like in the case of defects, because basically when you have a line defect, the structure of the two-point functions there are the same as the structure that you get in a CFT, but restricted to the line. And that's basically the same as taking this and setting x to 0. Now, an important point is that if we start from this OPE for the Euclidean Green's function and continue to the retarded correlator by going through this analytic continuation, this definition, then one, and again set x equal to 0, then this OPE expansion of the Euclidean correlator leads to this OPE expansion of the retarded correlator, which we may call a retarded OPE. And the important point is that there's this sign factor that basically comes by evaluating this difference doing these analytic continuations. Okay, and this sign factor is important. It implies that in holographic theories, this retarded OPE expansion only receives contributions from the multi-stress tensor exchanges. Basically, the operators that appear in holographic theories in the OPE are two kinds. They're the double traces, which are like products of O and O with dimensions 2 delta plus J plus 2n. And these operators will be killed by the sign factor. And then there are the multi-stress tensor exchanges which have dimension ND plus corrections. Okay, so in holographic theories, this retarded correlator simply has a structure of a sum over multi-stress tensor exchanges. And now for the actual calculation of this WKB method of Caneggiati et al. Is more convenient, instead of talking about x equal to 0, to talk about going to momentum space and set momentum to 0 instead. So instead of working with the position space correlator, we can Fourier transform the spatial position to spatial momentum p and then set p equal to 0. And one can similarly write an OPE expansion for this object, which is a function of time and momentum, and then set momentum to 0. Again, it will have a series expansion in powers of t over beta. And again, one can argue that in holographic theories, this retarded OPE only has contributions from the multi-stress tensor exchanges. These coefficients are not exactly the same as the ones appearing here, but the idea is the same.
Simone, can I ask something? If in the previous slides, if the external dimension is integer, I guess your sign will also kill the multi-stress tensor terms, right?
Yes, the sign. Oh, sorry. In that, right. So that's the case in which you have to be a little bit more careful. In that case, when the dimension is integer, there is actually a mixing between multi-stress tensor, potential mixing between multi-stress tensor and these double traces, because they all have integer dimensions. And in that case, you can show that these OPE coefficients actually develop some poles, and the limit is still finite. So this expansion is still correct. But more precisely in that case, it will capture the OPE coefficient for some mixture of the multi-stress tensor.
Right. And the double trace term, they will not appear nevertheless, right? Because they will still have this exact.
I mean, it's still
it
will be an expansion in powers.
Yes.
The way you can do this explicitly is just to first do calculations with delta arbitrary and then take a limit to delta integer at the end, and then you can get this. Okay. Okay, and for the analysis of the bouncing singularities and these exponentially suppressed terms, it's useful to work in frequency space, as I said before. So that can be done by doing the Fourier transform from real-time t to frequency. And so then the OPE expansion in the time domain, which is what I wrote before, if you do naively a term-by-term Fourier transform of this, you will get an asymptotic series expansion in powers of 1 over omega. So the OPE expansion in frequency space looks like an asymptotic series expansion in powers of 1 over omega. It's asymptotic because so the OP in the time domain is convergent series, but this one is asymptotic because the Fourier transform brings in these gamma functions that makes these coefficients in the frequency space diverge. Okay. So this term by term Fourier transform just gives us this asymptotic series, and it misses the non-perturbative terms. But nevertheless, the structure, the large order behavior of this kind of series implicitly encode also those exponential corrections. Okay, so now let me review briefly the holographic setup, which I already mentioned before. So we start with this planar black brane background, and for now, I'm still focused on the case of the usual bulk scalar fields dual to local operator. So just put a bulk field in this background. Just the free action is given here, where the mass is related to the scaling dimension, and the equation of motion for this is this wave equation. And then going to the frequency momentum space, one has to solve this kind of equation. And here I already specialized to the equal 4. And to find the retarded correlator, what one is supposed to do is solve this wave equation with the infalling boundary condition at the horizon, which means that you have to impose this condition at the horizon, and then look at how the solution behave near the boundary. It will have two fall-offs of this kind, and the retarded correlator is given by the ratio of the coefficient of the normalizable and the non-normalizable mode. Okay, so this is the general recipe to compute holographically the retarded correlators. Now, as an aside, let me mention that this wave equation in general does not have a analytic solution, but it can be mapped to, as was shown recently, it can be, well, actually, the fact that it can be mapped to the Hoyne equation was known, but it was shown recently that one can formally write a solution to this wave equation as a sum over supersymmetric instanton partition functions, which at least in some sense gives an analytic solution, but using that in practice is very hard because it's an infinite sum over instantons, and also there is no really small expansion parameter in the case of the planar black hole. So there is a sum over instanton which goes like in powers of some parameter, and that parameter is just 1/2 in the case of the black brane, and so there isn't really a way to meaningfully truncate that. And in any case, even if there was, it's very hard to extract explicit analytic answers from that supersymmetric instanton sum, so especially at large frequencies. So we will not use this method, but I just wanted to mention as an aside, and we will instead now turn to this WKB method of Caneggiari et al. To extract a large high frequency behavior. Okay. Okay, so basically we want to solve this equation, and the idea is that at large frequency we can try to do something like a WKB approximation. So we make an ansatz, WKB ansatz, like this. So kind of similar to what we do in quantum mechanics, where not the parameter which is large here is the frequency, and we don't take the mass to be large. The mass is fixed. So we can take an ansatz of this kind, and then this leading term is, as you can see by plugging this into the wave equation and seeing what you get, the leading term as expected is related to the time shift of a null geodesic. Null because in this large frequency limit, the mass is subdominant and two leading orders are like null geodesics. So this is kind of qualitatively roughly the idea, but in practice, as I said before, this WKB ansatz really breaks down near the singularity, and one has to do a more precise analysis there. Okay. So I'm going to try to go over the logic of their paper. As I said, it's a little bit complicated, so I'm not sure if I will succeed to explain everything. But let me try to summarize the main points of the logic that they have, because it's somewhat indirect, and a little bit convoluted. So first, to kind of understand some features of their main logic, it's useful to go back to just the boundary observables, and just think about the Fourier transform from the retarded correlator in real time to the retarded correlator in frequency space. So this is the integral that one would have to compute, say, if you knew what this object was. And suppose you want to know what's the large frequency behavior of this integral. Now, this is an oscillatory integral, so it's a bit hard to analyze. So one standard way to analyze the large frequency behavior is to try to rotate this contour. So in this picture here, I'm showing the complex time domain, and sorry, something went completely on top of my slides. Give me a second to take that away. All right. Okay, so the contour that gives the Fourier transform runs along the real time axis here. You can imagine rotating this contour to the imaginary axis, which gives this, instead of Fourier, gives this kind of Laplace type integral. But the price of doing that is that if there are singularities in the complex plane, you will also pick up contributions from there. So the red contour the contribution of that contour will be equal to the contribution of the blue contour, which is the sum of this plus contours encircling the singularities. Okay, and this contribution of the singularity will give the non-perturbative terms at large frequency that we are interested in. So if this singularity was sitting, say, at some Tc, then in general, that procedure of encircling that singularity will give a contribution which goes like e to the I omega Tc, which eventually will lead to those non-perturbative terms. Okay. Now, one observation is that if we write this, the full answer as perturbative plus non-perturbative part, where perturbative means, powers, series in powers of 1 over omega, and non-perturbative means these exponential corrections, then one can see that the contribution of going along the imaginary axis here just coincide with the perturbative part, because this is a convergent Laplace type integral, and you can just expand it term by term at large frequency, and so it does not contain any non-perturbative terms. So this maps directly to this, and the contribution of the singularities map directly to this non-perturbative part. Okay, so the proposal of this paper is that instead of computing the actual physical infalling solution, which would compute this whole thing, first they try to understand what would be the bulk procedure that computes just this perturbative part, which corresponds to integrating along this axis. And the integration along this axis is like a steepest descent contour from the point of view of this integral in time. And their proposal is that this should correspond to a steepest descent contour for the WKB problem in the complex R plane in the bulk. And then, by construction, this steepest descent solution of the wave equation will be differing from the actual physical solution we're interested in by non-perturbative correction. So essentially, this physical infalling solution is the one that computes the whole thing. The steepest descent solution is the one that computes just this perturbative part. And through a series of clever arguments, they find a way to compute the steepest descent solution and then indirectly infer what the physical infalling solution is. Okay. See, how much time do I have? Still like 25 minutes? Yeah, okay. So as I said, this is a bit complicated, so I'll try to go over it, but it's likely that will not be, all of the steps will not be completely clear. So if you have questions, interrupt me. But the main important point is the end result, but I'm trying to give an idea of how it works. So explicitly, if one looks at what those steepest descent contour look like in the WKB problem, the steepest descent contour are actually curves in this complexified radial variable plane that go from the ADS boundary to a complex fake horizon that is down here, r equal minus IH. So there are steepest descent contours that you can find by analyzing the WKB problem. It goes from there to there. And the solution built along those steepest descent contour is regular as you approach this complex horizon. Okay, so in order to connect that to the infalling solution, they basically deform the steepest descent contour to run instead along this contour shown here, which goes from this complex horizon along the imaginary axis close to singularity. And here you have to do a dedicated analysis and then rotate. So you start with the solution regular at this point, go up and then solve the equation here and rotate to the real axis. And then when you're far enough from the singularity, you can start using the standard WKB ansatz that I showed before. You match that to the near singularity analysis. You keep going, pass through the horizon with a high epsilon prescription, and eventually match to the near boundary expansion. So this procedure gives this steepest descent solution. Okay. Okay, so this is what I already said in words. And then once you have the steepest descent solution, the idea is that they can indirectly reconstruct the physical infalling solution by requiring basically that the steepest descent and the infalling solution differ only by non-perturbative terms, and that the steepest descent should give only perturbative terms and no non-perturbative terms. So as I said, the logic is a little bit roundabout, but it's a clever trick to construct the infalling solution. Okay, so now the details are not too important, just to flash what's going on. So near the origin, as I said, the WKB ansatz, the naive one, breaks down because essentially these terms are not small compared to the leading ones. And so instead of using this ansatz, one has to solve the wave equation in a double scaling limit where r goes to 0, omega is large, but with this product fixed. And this specific structure is dictated by looking at the regime of validity of this, just seeing where it breaks down. It breaks down when r is, too small compared, given by this ratio, okay? And in this scaling limit, the wave equation reduces to something like this. So in powers, again, you take the scaling limit and then omega is large. So x is fixed, but omega is large, and you get this kind of equation. So to leading order will be just this equal to 0, but then here I'm already including subleading corrections. And the nice thing is that this can be solved analytically in terms of Bessel functions. So you first solve this along the imaginary axis in that picture that I had before, imposing that the solution is regular as you approach that complex horizon, and this gives the solution. Then you rotate to the real axis, which gives this linear combination of two Hankel functions. And this now on the real axis give two modes, one ingoing and one outgoing. And the relative coefficient is what we can interpret as this reflection coefficient. So the picture here is a bit different from the one from the two-sided correlator. The reflection kind of happens as we continue from this imaginary axis, kind of behind the singularity, and then to the real axis, we get this linear combination of ingoing and outgoing modes. So this is the leading order result, like dropping this term. If one includes the contribution, the subleading term, you can do it. The details are more complicated. Let me just highlight the final result that you can basically fix this reflection coefficient up to the subleading order, which is this fractional power of the frequency. And this is all completely explicit stuff that you can extract by solving these equations. Okay, once you have this, as I said before, you start matching with the going away from the singularity where you can apply the usual WKB. So you do the WKB ansatz, which if you plug into the equation looks like this. And then as usual in WKB, like in quantum mechanics, you want to match this WKB with the behavior of the solution near kind of the turning point, which in this case, the role of the turning point is basically played by the singularity. So matching this to the structure like this. To do that, you have to look at how this WKB ansatz behave as you approach that transition region. So you go close to the singularity, but not close enough that this breaks down. And on the other side, you move far from the singularity, I mean, a little bit far from the singularity in such a way that you approach this behavior. So it's like WKB when you match, like the WKB ansatz far away from the turning point to the area function near the turning point is sort of like that. And then by doing the matching, you basically find that the WKB answer, as you start going away from the singularity, has two pieces, the minus and plus piece, again, like ingoing and outgoing, with this reflection coefficient, which is inherited from the solution in the interior by this matching. Okay, and then you start going away towards the boundary, where this WKB solution now behaves in this way, which approaches the behavior of the well-known solution near the boundary, which is given by linear combination of Hankel functions, when nu is... There's a question, Alessia?
Yeah, sorry. Just because I'm trying to keep track of the bigger picture. So
Yeah.
I would have thought that if you're studying Wilson lines on the boundary, then you would be considering some sort of extended worldsheet like object and the bulk.
Yeah, well, I'm not there yet, but
I see.
I'm all reviewing the case of you just their setup, because then the
Okay,
calculation
sorry.
will be same. So I'm not there yet. Yeah, it's taking a long time. I'm not in the I'm not in the Wilson line yet.
Okay.
Yeah.
Okay, sorry about that. Thanks.
So we can get back to that question later, maybe. Okay, so the next step is, as I said, is to match the near boundary expansion here with this WKB, and this fix the coefficient of this C2 in terms, again, of this reflection coefficient, which is descending from the original analysis near the singularity. So by this series of matching steps, we end up with this behavior of the steepest descent solution near the boundary, which is a combination of H1, which is a infalling mode, and H2, which is an outgoing mode. This H2 has this structure where R is the reflection coefficient. And this part basically agrees with the infalling, the perturbative part of the physical infalling solution. And so this relation tells us what we expect, that the steepest descent solution differ from the infalling solution by some non-perturbative parts, which have been computed through this matching procedure. Now, this is just a perturbative part, but if one also restores the non-perturbative part of this, which is not captured by this calculation, but it has to be there in the full solution, then one can write a relation like this: the steepest descent solution as the perturbative part of the physical solution plus non-perturbative plus this term that we have derived from the matching with the interior. And then the final step of the logic is to impose that the steepest descent solution, which is supposed to correspond to the steepest descent at the boundary, only gives the perturbative part of the correlation function, which means that this non-perturbative part of the infalling solution that we're interested in must be equal to this. So that's the final result of their logic. As I said, to me it's a little bit conceptually a little bit complicated at first to digest, but that's the end result. So after all the dust settle, you basically have this prediction for the infalling solution near the boundary. So you just use this identification, and then this is the physical infalling solution, where you have Enkel 1 and Enkel 2, and Enkel 2 is this outgoing mode, which has this reflection coefficient. And from this now, finally, you can extract the retarded correlator by expanding this at large R and taking the ratio of the normalizable and non-normalizable mode. Okay, and that's the result. and this gives these non-perturbative corrections. And here I only kept the leading one of the perturbative expansion, which comes from this analysis, but that can be improved by adding the series by doing the near boundary analysis to higher orders. Okay. Okay, so then the bouncing singularity follows by doing the Fourier transform. So all the details that appear here, not just the exponential, but all this, the details of this reflection coefficient, gives us all the detailed structure of the bouncing singularity. So the power is just fixed by the exponential and the location, but the coefficient of the singularity comes from the details of the reflection coefficient. So this is the leading term, and this is the subleading term where this stuff comes, ultimately from that analysis near the singularity of the black hole. Okay, so in that picture that I showed before, that singularity that was there is this explicitly this TC that I'm talking about here. So when we rotate the Fourier transform, the contour from here to here, we get the perturbative part plus this non-perturbative part, which comes from this singularity, these branch cuts. Okay, so that's the general picture. And so another remarkable fact is that this has consequences for the OP. If you study, you recall what the OP expansion of the retarded correlator looks like this, then requiring that, this should be consistent with the presence of the singularities by analytically continue, the function defined by this convergent series, by analytically continue it in the complex plane, you get a constraint for how this OP coefficients behave at large order, at large n. And this is a calculation which is technically a bit involved, but you can do it. And this is the prediction. So all this structure, which comes from this WKB analysis, implies that these coefficients should behave like this in the large n asymptotics. And this can be precisely matched with the near boundary expansion. So now I think I'm going to go quickly over this because I still need to get to the Wilson line. So to get this OP coefficients, as I mentioned before, you can do this near boundary analysis of Fitzpatrick and Wang. This was done recently in these papers. And so you solve the wave equation order by order near the boundary, and that gives you all these OP coefficients in principle to any order that you want. And going to sufficiently high order, like hundreds, you can do a fit and see that the large n behavior precisely agrees with this complicated structure, including all these subleading terms, which is very non-trivial. Okay, so now let me go back to the Wilson line. So the system I have in mind is n equal 4, where we can consider this Maldacena-Wilson loop, which couples the gauge field and scalars. That's the general case, where x is a contour and theta parameterize the coupling to the scalar fields. And I'll take the fundamental representation for the trace. The operator I'm interested in is the simplest example of this family of operators, which is the HTPS straight line, in which we take the contour to be just a straight line along the time direction. First, let me stay with Euclidean time for now, and later go to real time. And then taking the scalar coupling to just be pointing one direction. So this operator just couples to one of the scalars. And one can show that this is a conformal line defect in this theory. It preserves these bosonic symmetries. SO3 is the rotations around the line. SO5 are the rotations of the 5 scalars that don't couple to this. And then there is a conformal symmetry, one-dimensional conformal symmetry along this line, which is SL2R or SO2, 1. And so what are the defect correlators in this system? They're just objects of this kind where we insert like matrices inside the path order trace. So there are matrices at positions along the line. So this is a bit schematic. The path order will insert this Wilson line factor in between the operator according to the path ordering. And these objects are constrained by the one-dimensional symmetry, as I said before, in the usual way. So they behave like a one-dimensional CFT in a sense. And among all the possible operators that you could consider, there is the simplest and in some sense most important are these ones. They're so-called tilt operators, which correspond to the scalar fields that don't couple to the Wilson line, and those have dimension 1. And then there are the 3 displacement operators, which will be my main focus, which have protected dimension 2, and they describe the transverse deformation of the Wilson line. Okay, now we want to consider this at finite temperature. So first we can go to the Euclidean finite temperature theory, and then the defect 2-point function, will be what you expect. The Wilson line becomes a Wilson loop, Polyakov loop along the Euclidean time circle, and the 2-point function is just this Euclidean time-ordered 2-point function with of insertions on the Wilson line. And then we can go to real time following the similar procedures as I explained before. So in particular, the retarded correlator will be given again by this kind of commutator that you can get from starting from this, defining Whiteman functions and so on. And we will be interested in the case where this operator is the displacement operator, which, as I said before, describes basically the response of the probe charge to the drag forces in the finite temperature plasma. Actually, this kind of observable was studied long ago when there was a lot of activity studying quark-gluon plasma holographically. And there's this paper by Son and Tini in 2009 where they study precisely this system, but they were interested in the low frequency regime of this correlator, which is more related to the physics of like Brownian motion, transport coefficient, diffusion, and so on. Well, in our story, we're interested in the high frequency regime of this correlator, which was not studied before. Okay, so holographically, what is the Wilson loop dual to? So we have to find the minimal surface which ends on the operator at the boundary. So at 0 temperature, this is very easy to find. It's just a static string and which extends a long time, and the ADS radial direction, and the worldsheet is just an ADS2 at 0 temperature and embedded in ADS5. And the conformal symmetry of the line defect is reflected in this in the geometry of this ADS2. Now, this setup can be used to compute correlation functions in this defect CFT at 0 temperature, and it has been used extensively, starting from this paper that I wrote with Radu and Arkady. So basically, you start with this worldsheet, study its fluctuations, and then the fluctuation of the transverse coordinates are dual to operator insertions on the line defect, and you can study correlation functions in that way. In particular, the transverse fluctuations within ADS, there are 3 transverse directions. Those are dual to the displacement operators from the point of view of the line defect at the boundary. And the fluctuation of transverse coordinates in the phi sphere are dual to the tilt operators. Okay, so that picture, the basic picture is the same when we go to finite temperature. And when we go to finite temperature, all we do is changing the ADS5 to cross S5 to the planar black hole. So there's the planar ADS5 black hole and the S5 part. And then the dual of the Wilson loop in this setup is just the same static string, but now in this finite temperature system. So here's a schematic picture. We have this heavy quark probe at the boundary. So this is a fixed time. If you let time run, it will describe the line defect. And then we have the string stretching from the boundary all the way down to the horizon. So the worldsheet is basically just a 2-dimensional geometry extending around the time and radial direction of this 10-dimensional bulk geometry. Okay, so that's the geometry of the worldsheet. It's basically just this part of the space-time. So it's a 2-dimensional black hole in a sense that has a horizon, which is the same as the horizon of the bulk space-time. And the defect correlation functions can be computed by studying the dynamics of this space. So by that I mean, so this is actually some worldsheet embedded in the higher dimensional space, so you can study how it fluctuates within the higher dimensional space. But effectively, the dynamics of those transverse coordinates boil down to some two-dimensional field theory on this space. In more detail, you can start with the Nambu-Goto action, for the string, expand that around this static string solution, using a static gauge where the longitudinal coordinates don't fluctuate, and then expanding this to quadratic order, this reduces to some two-dimensional field theory on that induced metric, which is denoted by H here. So H is the metric of this two-dimensional space. Okay, so as I said before, there are 5 transverse coordinates on S5, which are massless and are dual to the tilt operators. And then there are 3 massive modes, which are dual to the displacement operators. And a feature which is different from the case of the usual box scalars is that the mass is radius dependent here. But that does not cause any qualitatively big difference in the analysis of the wave equations. It still falls within the same class of differential equations. In particular, you still get a Hoynes equation. Okay, so that's what the equation looked like. I already said about the real dependent mass. So I think, according to the time, I only have a minute, but can I go a little bit longer? Is it okay?
Yes.
Yeah, sorry. Okay. Well, I'll try to be quick. So as I said, this is also a Hoynes equation, but that approach is not very practically useful for our purpose. So we use the same method as we used before. So basically, the technique is the same, just the interpretation is different. Now we are solving some wave equation, which is describing the transverse fluctuation of the string. But mathematically, it's still a wave equation of the same kind, and we can still apply the same kind of WKB analysis following the paper by Caneggetti et al. Okay, so this is just summarizing the picture. We want to solve this wave equation with the infalling boundary condition at the horizon, same prescription. The solutions to this will have 2 possible fall-offs, where now delta is 2 for the displacement operator and D is 1, because the effective dual theory is this one-dimensional theory on the line defect. And the picture is basically this. So we start with the static string, but then we study propagation of waves, describing the transverse fluctuation of that string. And we solve the wave equation for that with the infalling boundary condition at the horizon. Okay. Okay. This I can skip, but just in words that I mentioned before, the small frequency regime was studied before. So just for completeness, let me mention what is known in that limit. The correlator goes like that. But I will be more interested in the large frequency, where we can use the same method of Caneggetti et al. There's just some slight differences in some of the details, but basically it goes the same way. So I'm not going to go through the logic. It's the same kind of logic. You solve the equation near the singularity of this space, this two-dimensional space, which is the same as the singularity of the bulk black hole, basically. And by that series of matching steps, you end up with this infalling solution, where the reflection coefficient is given explicitly here. And then you can get the retarded correlator for the displacement operator, which is given here. So you start like omega cube, because the dimension now is 2 and D is 1. So the power of this is like delta minus D over 2 in general. And now delta is 2 and D is 1, so that's 3/2. Sorry, the power is 2 nu, so it's 2 delta minus D, which is 3. Okay, so we see from this procedure, we get the exact same exponential, which is not too surprising a posteriori, because the wave equation that we're solving has a very similar structure. It's just some slight difference. But if you do a WKB approximation here, the leading term will still be controlled by the time shift of null geodesics in this space. but the null geodesics in this space are just the null geodesics along the radial direction, which are the same kind of null geodesics that appear in the analysis of the bulk scalar fields that I reviewed before. Okay. So from this, we can get, again, the bouncing singularities, which looks now like this. So to leading order, it's not a branch cut, it looks like a pole, but actually if you include the subleading terms, it is not a pole, it's actually a branch cut because there are these fractional powers here. Okay, and again, you can match this with the OPE expansion. And the OPE expansion for these defect correlators takes the same form as the OPE expansion for the parent for the CFT in the dimension just restricted to d equal 1. So the formulas are the same as the one I showed before for the OPE at x equals 0, basically. And they look like this. And the idea is the same. If we just focus on the retarded OPE, there is, again, this sign factor. And one can see that this OPE is, again, just controlled by operators of dimension n times d. Now, what are these operators? So if we think about what kind of operators can appear in the OPE of two displacements, well, there are the analog of the double trace operators, which here we shouldn't really call double trace because these are operators inserted inside this Wilson line, but we can call them as two particle states that are like bound states of this effective scalar field, which is dual to the displacement operators. And schematically, these are like inserting operators of this kind inside the Wilson line, and they have dimension 2 plus 2 plus 2n. Okay, and then there are these operators of dimension nd, which appear. And the reason that they appear is clear if you just look at the structure of the wave equation, because it goes in powers. If you look at the near boundary expansion, it goes in powers of r to the fourth. So for d equal 4, so there are the same kind of operators, the same kind of dimensions that appear in the case of bulk scalars. What is their interpretation in this context? Well, our interpretation is that these are basically just the defect analog of multi-stress tensors. They're basically what you get if you take the bulk to defect OPE, which is a limit in which you take a bulk operator to the defect. If you take that kind of bulk to defect OPE of the multi-stress tensors. So basically, they are like multi-stress tensor, but attached to the Wilson line. So it's some kind of higher trace, multi-trace version of the defect operator where you have the trace, the path order trace, but then you also attach this trace of stress tensor to the n, to the Wilson line. And physically, you can think of this as bound states, in the bulk, as bound states of multi-graviton states and the string worldsheet. So the interpretation requires some thought, but the mathematics is the same as the one you see for bulk scalars. You still have this OPE expansion that goes in powers of nd or 4n in d equal 4. Okay, and you can do the same analysis that I did before to deduce what this kind of singularities imply for the large order behavior of the OPE coefficients. And this is what you get. And again, you can match this precisely to the near boundary expansion. In the near boundary expansion, you can compute all these OPE coefficients order by order and go to very high order, skip back, do a fit. Here, just show explicitly what kind of thing you get. So you can do a fit by putting an ansatz including integer and fractional powers as suggested by the prediction of the WKB analysis. And then you can do a fit and you find that all these numbers precisely agree with this analytic prediction. So again, the structure of the large n behavior of the OPE coefficients is precisely consistent with the presence of this bouncing singularity in the defect correlators. Okay. Now, another thing that you can do, which I think is good to do because the calculation that leads to these non-perturbative terms as I try to explain, is complicated and it follows this logic of the paper by Anijadi et al., this WKB matching and so on. So it would be very nice if you could actually see these non-perturbative tails from numerics. And we checked that this is in fact true. You can numerically solve just the wave equation with the usual physical unfolding boundary condition, and you can find the retarded correlator. You can plot its real and imaginary parts. So the numerics here is this blue solid line. This is what you get by solving numerically the differential equation. This red dashed line is the prediction of WKB. So it's basically this, the omega q plus this non-perturbative term. The oscillations are because, there is this I in the exponent. So when you take a real and imaginary part, that gives sine and cosine multiplying the exponential. Okay, so this is for the real part, and this is for the imaginary part. And the orange dashed line is the analytic small omega result that Son and Tini computed long ago. That's just to make sure that the numerics is correct. That matches also here at large, at small omega. Okay, for the imaginary part, everything is saturated actually by the zero temperature result. So to see better the contribution of these non-perturbative tails, one can plot the imaginary part subtracting away the perturbative piece, which is like omega cube plus the power of the series. And then what you should supposed to see is just these oscillations modulated by the exponential decay. And the agreement is extremely good, so again, the dashed red line is basically plotting this, the imaginary part of this. And the blue line is the numerical solution where we by hand subtract the perturbative part, which is this plus the corrections that you can get from the near boundary expansion. So this gives us, very good confidence that all the details here are correct. There's a reflection coefficient, which is quite complicated, and it comes from the analysis near the singularity. Must be correct, because otherwise we wouldn't see such good agreement with the numerics. Okay, I think I'm kind of over time, so let me just summarize. So first, I reviewed the case of thermal retarded correlators in holographic theories, and we showed that they have bouncing singularities. Not we showed, but I reviewed that they have bouncing singularities at this location, and these are in frequency space are related by these non-perturbative tails, which can be computed directly by this WKB method of Afghani-Jadi et al. And the singularities are from like a complementary point of view. They are controlled by the Largen asymptotics of multi-stress tensor OP. And the agreement between these two approaches, I think, is quite remarkable, because this approach only really cares about near boundary expansion, but this approach actually involves solving a wave equation near the singularity and doing complicated analysis in there. And then I extended this to the case of defects, considering retarded correlator of displacement operator on a Wilson line. And we found that holographically, to leading order strong coupling, which is what, the regime I considered, the same complex time singularity appear in these defect correlators. Again, the non-perturbative terms can be computed from WKB. And again, there is precise agreement with asymptotics of the OPE coefficients, where now what controls the singularities is basically a sort of defect analog of the multi-stress tensors, which we can think of as multi-stress tensors attached to the Wilson line. And again, there is a precise agreement between these two approaches. Okay, I think I'm already 12 minutes over time, so let me just leave this slide here and ask for questions.